In your experience, you've probably noticed that if you're, say, on a swing, there is a best time to try to swing your leg so you get the biggest swing possible. Or in another example, if you're bouncing on a trampoline or on a bed, you might also find that hitting the mattress, for example, at certain rates are more effective in making you bounce than others. So this problem is basically going for that and trying to say, suppose that you had a mattress and a rambunctious baby bouncing up and down, and in that discovery process is figuring out when it's best to bounce and at what rate to bounce off there and try to get the biggest jumps it possibly can. So what is going on here? Well, the setup also tells us a few other things that we are mentioned. The mass of the baby at 12.5 kilograms. So this is definitely not a newborn. And also we're supposed to treat the crib mattress basically as a spring. And we are told it has a spring constant of 700 newtons per meter. So first off, if we're bouncing up and down like that, we have a spring, we should be thinking this is simple harmonic motion. But also the baby is supposed to be jumping, so the baby's applying additional force. So this is actually forced oscillations. So in that case then, if we're trying to figure out when it's best to try bouncing on the crib, there are two things to consider. What is the normal frequency for this bed? What is its natural frequency? And then the frequency that you, or in this case the baby, is exerting forces. So the first thing is we have to realize that if we're doing a forced oscillation, what describes the amplitude of a forced oscillator? Now we've learned that the amplitude itself is given by this expression, which of course looks quite scary and messy, but here's what we know. We know the mass of the baby, we know the spring constant we're giving for our system here. What we don't know, of course, is what is the force applied, and also we're including the variable b here, some sort of dampening. We don't know what that is, it's not given, so it seems like we have a lot of unknowns in this expression. But what we are trying to find is a maximum amplitude. We're trying to get the biggest possible bounces. So if we realize that, for example, b here is a constant, mass is a constant, this term is a constant, and omega naught here is the natural frequency, and that frequency is related to the square root of spring constant over mass. So those terms aren't going to change depending on how hard or how fast the baby is oscillating. So really the only variable that we can change down here in the denominator is going to be the frequency that the baby is actually oscillating, or I should say the angular frequency here. So we see though that if these two frequencies are the same, this will be 0, and that's pretty much the smallest we can get the denominator to be, and the smaller the denominator, the larger the amplitude then. So all we need to do then, it looks like, is basically set omega equal to omega naught, and that will tell us when it's best and where we're going to actually get resonance. So what this whole thing is really all about is two things: forced oscillations and resonance. And I won't spell that out because I'm horrible at spelling. So in that case then, for part A of this problem, we're trying to find what's going to be the best frequency for this. So we realize if we have angular frequency here equal to the natural angular frequency we're set. But we need a conversion, because the problem asks for frequency as opposed to angular frequency. And mind you that frequency is defined as the angular frequency divided by 2 pi. So, all this doesn't mean too much though. It's going to be fairly easy to get this all in order. So let's just give ourselves a little bit of room to finish this up. And so the angular frequency that we want is going to equal square root of k over m. The frequency we want, omega over 2 pi, or in that case, 1 over 2 pi square root of k over m. K and m are variables that were given, so we just plug that in, and we get about 1.2 hertz. Now, let's think and see, does that number actually make sense? Does it actually fit our intuition, our experience? So, about 1 hertz, so that means you're bouncing about once per second on a mattress, like on a bed. That seems fairly reasonable. You usually don't get that much bounce, so you're coming down and hitting it, on a fairly regular basis. So 1 hertz per second, that seems to be close to my experience. If this were a trampoline, that wouldn't make sense since I'd expect more bounce and there'd be a longer period between those sorts of bounces. Our equation even would suggest that on a trampoline you have a lot more stretching going on, so that would suggest, for example, a smaller spring constant. And if k is smaller, then the frequency is smaller, and so greater time between your bounces. So this number at least makes some intuitive sense. It seems to match experience to some degree. Now, part B of this problem brings up something you might have also experienced when on trampolines or bouncing on beds. There seems to be kind of a certain point where you start hitting the surface harder and harder and you don't really get any more out of it. Part of that is that once you have been ejected from the bed, once you've left the surface, it's no longer there to give you any sort of oomph. Basically, if you lose contact with the surface, then it's not pushing on you, and you only undergo then basic free fall. So this question, part B, then, is asking about the maximum amplitude you're going to have before you actually start losing contact. So how are we going to think about that? Well, think about it like this in the following way with a little bit of space. Instead of the baby here, let's imagine you just have some sort of a spring and a block. And let's suppose that the block isn't actually attached to the spring. Now, if the block were moving upward at some moment with some velocity v, there should be a couple different forces acting on it. If the spring is being stretched, then we would expect a force downward due to the spring, but that's only if we were attached. So that actually won't be the case here. So instead then, really this is just going to be the force of gravity acting on here. Now, the spring should of course be moving up as it unstretches, but if the block were moving fast enough, then it might be the case that it would leave contact from the spring. And the key thing there is realizing, well, the spring is only going to stretch so much because its own elastic nature is going to make it fall back to some degree. It's going to act on itself, it's going to accelerate down. So we realize if this block is actually undergoing more acceleration due to what the spring should do, as opposed to just what its weight would do, then we're going to actually lose contact. So basically then, the amplitude max that we can have is going to be that of acceleration due to gravity, or at least somehow related to it, some sort of proportionality to that. So in that case then, if we think about, well, what describes the acceleration of a simple harmonic oscillator, we remember that that acceleration is supposed to be the amplitude, omega squared, cosine, etc. And I'll just leave that as etc. because what we really care about is maximum acceleration, and when that is equal to acceleration due to gravity. So, this is basically then our limiting case. We see that at some point the amplitude becomes large enough that it becomes equal to that of acceleration due to gravity, that these accelerations become the same, and beyond that then of course we actually lose contact. So if in that case we want to solve for what that amplitude is, see then that that amplitude I should say, is acceleration due to gravity divided by omega squared, I should say. And this is going to be then that natural frequency related to the spring itself. And since we already defined what that's supposed to be, we see this is going to become G M over K. Now I haven't given myself too much space to plug in the numbers here, but we'll just move this a little bit off to the side and plug in our numbers, and if I put in 9.8 for acceleration due to gravity, I find that the amplitude size we're going to get, based on all the other information we have, is 0.175 meters, that is 17.5 centimeters, not even a foot, basically, less than a foot. And again, bouncing on a bed, you probably don't get more clearance than that. Don't expect the bed to really bounce up much with you then. So that at least makes some level, again, of intuitive sense. And again, all based on our stuff with simple harmonic oscillators and treating the bed that way.